Moving on to 1.6, which is on homogeneous systems, subspaces, and bases. So actually quite a bit to go through in this section. So first we'll talk about what's called a homogeneous system. And basically it's rather simple. It's a system of equations that's set equal to 0. And so you have this system, so AX equals 0 is homogeneous, and it clearly has a solution of 0, 0, 0. So you put in 0, 0, 0 for everything, and of course you get 0 equals 0. So that is always what's called the trivial solution. So the trivial solution is always a solution for homogeneous, so which implies that all homogeneous systems are consistent because there's always the trivial solution. Okay, so there's more to that. It's almost like a building block for other systems when you look at stuff, but we'll talk about it as we go here. So the next theorem is theorem 1.13, and it says this. So let AX equals 0 be a homogeneous linear system. And then if H1 and H2, so those are like column vectors that represent X, Y, Z, or X1, X2, X3, X4, X5, X6, or whatever, right? It's the ordered in tuple that's the solution we are representing now as column vectors for here. So I'm saying H1 and H2 are solutions of AX equal to 0, then so is their sum that looks like this. R, so a constant R, H, plus a constant S, H2, so that was H1, H2, for R and S in the reals for constants R and S. So let's look at the proof of this. It's highlighting to see where I'm stating things better as we go. So let's look at the proof. So let's let H1 and H2 and suppose that these are solutions to that system. So first we basically saying this is what's true to that homogeneous system. So let's do that. So let H1 and H2 be solutions of AX equal to 0. And we want to show that that sum is as well. And so basically we substitute in the A times that RH1 plus SH2. And then we use basically the matrix multiplication associative property and the distributive property for matrices. So you get A times RH1 plus A times SH2. And then we factor out R and S, so you get RAH1 plus SAH2. And let's say we multiply those first, but what are, excuse me, if AH1 is a solution to this system, then what is this product equal to? And what is this product equal to? Yes, those must be 0. So you get 0 for both of these if they are solutions to the homogeneous system. So that equals, we're looking over here, so that equals R times the 0 vector plus S times the 0 vector, which is, of course, the 0 vector. Therefore, that sum, and it's basically a linear combination, isn't it? So R and S is a linear combination of the vectors h1 and h2. So we can generalize this theorem, which is corollary 1.13. So let me finish this up. So thus, RH1 plus SH2 is a solution to AX equal to 0. And that's true for all S and R in the reals. So this type of argument that we just did here for the homogeneous system, where you have separate solutions, is also applicable to other contexts as well. In fact, if any of you are taking differential equations, this is similar to chapter 4 stuff, where you have two solutions to a homogeneous, it's for linear second order differential equations. It's essentially the same type of argument. It's it's different, but it's the same type of argument, because you basically get 0 and 0, and then since those are just zeros, they also will multiply and add up to 0, which is what you see in that as well. I think that's 4.2 in Nagel, just FYI. So this lends us to a general statement, which is corollary. So corollary is a result of a theorem, sometimes more pertinent, sometimes more general, depends. So corollary 1.13 says this. So that says every linear combination of solutions of a homogeneous system is again a solution. So, and I just did that in words. I believe they do too in the book. So every linear combination of solutions of a homogeneous system AX equal to 0 is again a solution. And we could write that out all nice and fancy, but basically it's this proves it. I mean, this essentially is in general. You could extend this argument to any size. So if you have H1, H2, H3, H4, H5, H, etc., up to n, then you have the same basic argument. This is that linear combination. So it's really saying the same thing. It's just rephrasing it, essentially, that it's true for every linear combination of solutions to a homogeneous system. Okay, let's move on to the next thing. All right, so next we're going to talk about the general concept of what's called closure. Okay, so this is the general concept of closure. And I'm saying it's because there's a specific concept we'll talk about for subspaces, but first I want to talk about the general idea. So I'm going to write down that. So general concept of what's called closure. Again, this is not a psychology class, so don't worry. Right, so general concept of closure is this. So we have two sets. So this is, think generally speaking, these are just two sets and an operation. So let A and B be sets. Maybe they're supposed to be non-empty and all that, but let's just say they're sets. And let's suppose that B is a subset of A. So that's subset notation, probably seen it by now. So so every element of B is in A, but not necessarily every element of A is in B. Excuse me. Now we're going to just say star. So star is a binary operation. So let star be a binary operation of elements of A, which would include B, of course. So a binary operation is pretty much everything you've seen. It's multiplication, addition, scalar multiplication of matrices. Anything you have basically two things, you operate on it, and then you get a result. Okay, so that's what we mean by a binary operation. So here's the idea. We say that B is closed under that operation if for AB in the set B, A star B is in the set B. Now, that is a arbitrary statement, right? I mean, A and B can be any elements in B, and you do the operation and it remains in B. It doesn't jump outside of that set B. Now remember, B is a subset. Okay, and I'll show you examples that it doesn't work. So B is not closed under that operation if there exists elements where you perform the operation and then it's not in B. So we say B is not closed under the operation star if there exists elements A, B in B such that A star B is not an element of B. Okay, so simple but subtle concept here of what this is saying. So for example, let's take the natural numbers, a subset of the real numbers. So the naturals, so let's just let A and B be in the naturals. Now, so 1, 2, 3, 4, 5, right? I mean, just remind you what the naturals are. So naturals are 1, 2, 3, etc. So if star was the operation addition, are the naturals closed under addition? So is A plus B always back in the naturals. Okay, for addition, that's true. So we would say that the naturals are closed under addition. Now, what about subtraction? And all we have to show is that there exists two elements in the naturals such that their difference puts you outside the naturals. And that should be, if you think about it, pretty obvious. So let's let 2 and 5, or we don't have to say let them be in the naturals, they just are. So 2 and 5 are in the naturals. Okay, we know that. That's comma there. So what if you subtract 2 and 5? So 2 minus 5 is equal to negative 3, which is not an element of the naturals. Therefore, we conclude what? So therefore, the naturals are not closed under subtraction, which is a binary operation, right? So that's the general I could go on and on, of course, on this. One of them to think about is maybe the reals and the complex, right? So you have a plus bi in the complex. So some of those value or elements in the complex are closed. So if you just choose or you let or suppose b is equal to 0, then you get all the reals. So a plus bi is an r, basically just a is an r, and any two elements in r stay in r when you add them, multiply them, divide them, subtract them. But if you take elements that are, so in other words, the reals are closed. So for any a, b, and r, a times b, a minus b, a plus b, etc., are still in r. So we would say the reals are closed under all of those operations. But R is a subset of the complex numbers. Okay, so think about that. I won't get too much into detail because we want to get into vectors and talk about vectors and eventually vector spaces, which we'll get to in the next chapter and stuff. So let's now talk about definition 1.16, closure and subspaces. So this is where this is leading to. That's the general concept of closure. Okay, so next, definition 1.16. This is on closure and subspaces. So, for subspaces, this is what we have. It has to do with essentially what we just talked about, but it has to do with vectors in general. So we say W subset of Rn is closed under vector addition if for all u and v in W, u plus v is also in W. So we would say that's closed for vector addition. So, and then we have closure for vector or for scalar multiplication as well. So, and then we say if, similarly, if RV is in W for all V in W, and little r is in the reals, well, it's a constant, then W is closed under scalar multiplication. So then W is closed under scalar multiplication. So so that's closure for vectors in Rn and subsets of Rn. So it's a subset. So this is a subset. Now we're going to define now a subspace. So a non-empty. So this is it basically. So a non-empty. So not the empty set. So non-empty subset W of Rn that is closed under both vector addition and scalar multiplication is called a subspace of Rn. So a non-empty subset of W of Rn that is closed under vector addition and scalar multiplication is called a subspace of Rn. So it remains in the set. So let's look at a couple examples of that. And it's kind of like the one I showed you up here for R. But those are just numbers. Those aren't vectors. But it's kind of similar. So if you have two numbers, A and B, in R, you do any of these operations and you stay in the reals. You don't like all of a sudden jump outside the reals. But that's not considered a subspace for this definition because this has to do with the vectors of R. We're not going into the complex plane. That's different, right? Okay. So let's look at a couple examples of that. So this one tells you, show that W equal to the set X negative X such that X is in the reals R is a subspace of R2. So is a subspace of R2. So we have to show closure, basically. That's essentially what you're doing. So close under the operation. So we need to show that you have closure for both addition and scalar multiplication. So what you do, and I'll come back to that, but move up here. So let's let U equal A negative A, and that vector is clearly in W, and let's let V equal B negative B, and that vector is clearly in W. And then you have to show both steps. I'll write it down. One, the question is U plus V in W? Like in general. So you got to show that operation. So let's do that. So U plus V is equal to, and then let's just do, so now you're just doing the basic operation of vector addition. So that's just A, negative A, plus V, which is B, negative B. And so you basically need to add them up and see if you get the same exact form. You have this and then a negative of the same thing. And that thing is in the reals. So you got to manipulate this a bit. So that's equal to, let's just go down. I think I've got space. So we'll just say it like this. So you say that's equal to, and now add them up. That's A plus B, and then negative A minus B, or plus negative B, I'd be even more precise, plus your negative B. And then you can factor that out, right? You can say that's equal to A plus B. So A plus B is just a real number. And then we can factor out the negative and write that as negative A plus B. So is that the form we're looking for? And you can see that it is. It's exactly the form we're looking for. So this and this are what we started with. And those have to be the same thing here and here. And then those are both in R. So this is in W since A plus B is in the reals, like it didn't jump outside there or something, and you have the right form with a negative in front. That's your first step. Now scalar multiplication. So the question is R V in W? Okay, so then let's let R, little r, be in R. Okay, so that's my scalar. And then you show it again. You say R times, did I use U? I used U. Doesn't matter. R times V is equal to R times B negative B, which is equal to RB and then minus RB. And basically same argument. That's true since RB is an R. So that's in W since RB is an R. So again, same exact form. So this form is the same as that. Real number, comma, negative, same real number. Right, so that's why it works. Okay, so because it satisfies the closure of both vector addition and scalar multiplication, we conclude it's a subspace. So therefore, W is a subspace of R2. So in other words, you do the operation and it remains in the set. That's the key part. Okay, let's do another example. All right, so let W equal the set XY such that the product of those components, XY, is less than or equal to 0. So this is W a subspace of R2. So is W a subspace of R2? Question mark. So let's check that out. right, so this one, well, let's think about it. What is that? What is this set? So we have vectors in R2, and you want their product to be negative. So this one, I think, takes some graphs. Let's do a graph. So you have X and Y. So let's think about this. So you have these different vectors, right? So in other words, is like this vector, is that a vector in that set? Okay, so is this product of those two values right here? If you do that product, is it negative? And the answer is no. So the ones that whose product is going to be negative is quadrants what? So this is quadrant 1, 2, 3, and 4. So we can see that quadrants 2 and 4 have a product that's negative, right? So it's this quadrant over here. Okay, so all of these vectors that end up over here have where their components end up being negative, right? And then this product. So so we're talking about the set, the subset of those elements. So if you did like this one, let's see, 1, 2, and then negative 1, 2, 3. So maybe down here. Okay, so that vector right there, I didn't do that right. I'm going to change that. So just do 2 and 3, which would be here. Okay, so that vector, so this is 2 and this is negative 3. That's behaving like that, right? So 2, negative 3. And then any vector up here also, I didn't want to do that, is in that set. So when you add vectors or multiply vectors in that set, does it remain in the set? So here's what you're looking for. So what is your intuition first? So find either two vectors whose sum is not in W or a scalar multiple not in W, where we have to, of course, start in in W. So you have vectors that you're starting in W, and then what happens? So this would be, say, 1, 2. So this is negative 3 up. Well, we'll just say 2. So this is negative 3, 2, right? I mean, it doesn't matter what it is. I'm just showing that those products are clearly negative. So after working through a few things, so you could maybe choose one. So see what you can figure out. So see if you can finish this. Okay, so finish. Okay, and then I'll give you a hint here and then work it out. So we're going to let U be negative 1, 2, and V be 2, negative 1. What happens when you add those together? U plus V is equal to what? You clearly see that's 1, 1. But 1, 1's product is positive, so that's clearly not in W. That's all you got to do. Therefore, W is not a subspace. So you just have to show 1. If you multiply, scalar multiplication is going to work, right? Basically, scalar multiplication is either going to make this thing longer, it's going to make this vector shorter, or it's going to reverse the direction, which would put it back in the other region, right? The other quadrant. So again, any vector in here is either going to stretch it, it's going to shrink it, or it's going to reverse the order, or direction, I'm sorry. So scalar multiplication actually works, but addition does not. Okay, so it's not a subspace of R2. Actually, you got to say of what? So of R2. Okay, let's move on to other stuff. We will stop there.